Another day we're going to discuss a very important topic titled oscillators. And by name is Joseph. Oscillators are electronic circuits that generate outputs. But then let me try to do the needful. An oscillator generally is something that can generate an action without necessarily having maybe something that is triggering it, maybe like power supply. Like when you have your car, and maybe you intend to travel somewhere and the battery is weak. Are you getting me? Yes. You can borrow someone's battery, start the car. And when you start the car, you can remove the battery. And the engine of your car will continue to oscillate. One, because the firing order of the system is maintained. Are you getting me? Yes. For that reason, the car will continue to move. It will move until you switch it off. Are you getting what I'm saying? Yes. So for this reason, oscillators behave like that. Another good example of an oscillator is oscillators and resonance are very close. Are very what? Close. Like resonance, we can say it is when maybe a body is agitating based on another frequency that is very close to it. For instance, you have your radio, you are listening to your radio, and then somebody just came with a machine, did not switch off the machine, and then the machine is on. You know that the vibration that is coming, the sound that is coming from the machine may be affecting your radio. You'll be hearing the humming sound, that kind of thing. Yes. As the machine continues to move away from you, then the frequency in which that vibration is taking place will now synchronize with that of your radio, and that's how they continue to exist until the distance, the proximity between the machine and the radio is also what diminished or finally collapsed or attenuates. That's another aspect. But that is resonance. But oscillation also has taken place at that moment. Another oscillation is you can find oscillation or oscillators in radio receivers at the tanker circuit, at the RF side of it, of your radios. We'll use oscillators at that level. One, you have a ferrite rod, you have the gang or the tuning capacitor. Normally, an oscillator is a circuit that usually have an inductor and a capacitor joined together. Then you have the resonance frequency, and that is oscillation, right? So at that level too, you have an oscillation, and that oscillation leads to a frequency, and that frequency is resonance frequency. Okay? Mm-hmm. And resonance frequency occurs when the reactance or the capacitance and the reactance or the inductance synchronize. When they synchronize, then you have what is called resonance frequency. Are you getting me? Yes. So today, we are privileged to see another good topic that is relating to that. And what we studied concerning operational amplifiers. Operational amplifiers are used in oscillators to generate outputs. So today, let us look at oscillators in detail based on the internet of electronics. Oscillators are electronic circuits that generate an output signal without the necessity of an input signal. Without the necessity of an input signal. In our human behavior, there are times that you behave like a mad person without somebody using you. We oscillate in our own nature. Have you ever imagined you sit quietly and then shout, "Kai!" Have you ever noticed that kind of thing in you? Yes. Somebody asks, "What's happening?" You say, "Don't mind." There is something that, in fact, we're induced naturally as humans, and we behave that way. So it's not just in electronics. And that's why there are some systems that when you switch them off, you look at them still being on. So now, we're also made to understand that there are several types of oscillators. These oscillators will produce sine waves. Oscillators produces many waves. Such as sine waves, square waves, triangular waves, rectangular waves, these are the kind of waves. There are many other ones that you may see. It will produce those things. And you see, these waves are meant for specific purposes. They are not just used anyhow. In a television receiver, we'll have another one, a sawtooth wave. Sawtooth waves. Sawtooth waves. Let me tell you something. For sine waves are mainly for this kind of radio receiver applications. Are you getting me? Square waves, you find them in televisions, triangular waves in television, sawtooth waves in television, even rectangular waves in televisions. Circuits. Intelligent circuits. So, when any circuit that can give you an output, maybe in terms of this kind of waves, is an oscillator. Okay? And I told you that oscillators don't necessarily need an input for an output to be produced. And this is achieved by using discrete components like transistors. And a coupler integrated circuit called the 555 timer is an IC that is used very commonly to achieve oscillator circuits. Very, very commonly. And we're going to study it today. But today, we'll be looking primarily on sinusoidal oscillators operation, and is based on the principles of positive feedback, where a portion of the output is fed back to the input in a way that causes it to reinforce itself and thus sustains a continuous output signal. What I'm talking about this positive this is this feedback. Let's consider this to be a black box, okay? This is your output, right? This is your input. And this is an oscillator, right? And if we set positive feedback, that is taking part of the output and bringing it back to the input, right? This is feedback. And we're saying here is positive, right? This is positive feedback now. For a positive feedback, the signal that enters the input has the same frequency phase and magnitude as the signal that is coming out of the oscillator. That is, an oscillator 1, inside this black box, there is a circuit that has an amplifier. And the amplifier could be a transistor, as I mentioned. Could be what? A 5-5 timer. It could be what? An op amp. These are some of the key active components that will be used inside the circuit. Any signal that enters this circuit here is amplified. And what are you going to get at the output? The output will be in phase to the input, but with that is the magnitude, amplitude of the signal being larger than what you have at the input. Are you getting my point? Yes. And this part of it is now fed back. Part of it is fed back. Part of it is fed back. And here too you have it like this. It is feeding back to reinforce what is going in initially at the input in order to avoid attenuation. You get the back. That is just a simple principle, but we are going to discuss a more deeper one than that. I want to let you know that oscillators are widely used in many communication systems, such as in digital systems, including computers, to generate required frequencies and timing signals. Oscillators are used in computers, in digital systems. Also, oscillators are found in many types of test instruments like those used in the lab, like a function generator. Function generator is an instrument that is used in electronics to generate waves. It can generate square wave, triangular wave, it can generate sine wave, square wave, triangular wave, rectangular wave, even so it can generate. And the instrument is called pattern generator. And there's another one that we call audio generator. That one generates only the audio signal. And the audio signal is purely a sinusoidal, gives you a sinusoidal waveform, a waveform like this. Sinusoidal is sinusoidal waveform. This type of wave. This is the type of wave that gives you something like this. Let us look at the positive feedback sample diagram that produces oscillation. Positive feedback, okay? Non-inverting means it's a positive, something is connected to the positive side. Are you getting me? We were studying this yesterday, you know that we are going to apply today. And this one is the feedback circuit. Feedback circuit. CCT means feedback circuit, right? So now, you may have this kind of waveform. You have the one at the output should always be lighter than the one at the input, right? Tell you that there's an amplification, there's an amplifier inside that box. And then this one also, it will feed back. Are you getting my point? And these two waveforms are said to be what? In phase. And what are conditions for oscillators to take place? For oscillation to take place, what are the conditions that are required for oscillation to take place? 1. The first shift around the loop is always 0 to take place. 1. Conditions for oscillation to take place. The first one is that the first shift around the loop is 0. In as much as the input signal and output signal are changing, they are changing at the same time. They are synchronizing and changing at the same time. That is, when the input is at positive, the output is also at positive. Are you getting me? Yes. So they are always changing. If the output is at 0 reference, maybe here is a 0, right? It's 0. At that same time, that's where the other one too will be. So the first shift around the loop is 0. It is not 0. If the other one is 2 or 20%, it's 20, will you have the same waveform? There will be a difference. So the first shift around the loop is always what? 0. And the second condition is that the gain, the closed loop gain, is always 1, 2. Is always 1. Any gain that is more than 1 will cause a serious distortion. But there is something about these oscillators. When you start an oscillator circuit and oscillation begins, the gain will go almost above 1, but then finally come down and rest at 1. That is when the steady state operation of that oscillator will begin. Are you getting me? Yes. Imagine your car. When you start your car, without engaging the gear, the sound is usually what? Very high. Those of you that know how to to drive, even on motorbikes that you have, the sound is usually what? Very high. The start-up is usually always the problem. Like when you look at issues of motors, the starting speed is usually what? Very high. But the running speed usually looks about to be almost very steady. Are you getting what I'm saying? So there's a running speed and a steady state speed in which everything is required. So in this case, when you start your car, the speed is very high. I mean, the sound goes very high. But after some time, when you engage the gear, you hear yeah. So when, as you continue to accelerate and engage the gears, the sound will be more smoother. You know, that is, you will be enjoying it. Like for the automatic, it will be selecting itself, telling you that yes, what you are doing. At least I'm selecting it to give the engine some kind of rest. So that is how oscillators to behave. So if you start off an oscillator, even if it's supposed to be a 1, let's say this is your 1. This is your 1. Do you know what it will do? The oscillator, before it begins to oscillate normally, maybe it will go like almost up. And then it will go up. And then calm down and then start. I don't know if you have gotten the point I'm trying to make. Then it will shoot up. Then after some time, it will go on a steady state. The first thing, when somebody slaps you, the first thing you shout before you start crying no more. Abi? Cry! Then the cry goes normal. That's the normal thing now. You don't just start crying loud like that. You start once and then create awareness around you and then begin to modulate it. And if that is denoted as B, there is something key that we need to understand about this. If the attenuation is, e.g., if the attenuation of an oscillator is 0.01, 01, comma. The question is, how can you get that unity gain if the attenuation is up to 0.01? That is, when the signal that is being fed back has come down to 0.01, how are you going to get a 1? Are you with me? Yes. If the feedback signal now B tends to be 0.01, how are you going to get a 1? That's the question I'm asking. You don't understand what I'm saying? The voltage gain, here the voltage gain, LV, equals to the closed loop. The closed loop here is A times B. And that should be 100 times 0.01. And that will give you the voltage gain of 1. Are you there? Yes, Startup conditions. What are the conditions that are required for oscillators to start? One, I mentioned here, I told you that the phase shift or the closed loop must be equals to what? 0. And the closed loop gain is always what? 1. Those are the startup conditions for oscillations to take place. And then if I should ask you what are the conditions required for a circuit to oscillate, these are the conditions. Have you seen it? Yes, and if I say define positive feedback, will you tell me that the signal that is feeding back is in antiphase? Is it in antiphase? In phase. Are you there? So let us look at oscillators with RC feedback circuits. When you say RC feedback circuits, what do we mean by that? Now we're looking at type of oscillators, right? Huh?
Yes, sir.
oscillators. RC feedback circuit oscillator. What is RC? R here implies resistor or resistance and then capacitance. Capacitance. Are you getting me? When you have a resistance and a capacitance connected in a network, it can either to lead to, it can result to a lead or a lagging circuit. An RC network could result to lead or lagging circuit. Could result to lead or a lagging circuit. And we have types of these types of RC feedback circuits. We have the Wayne-Bridge oscillator, the first shift oscillator, the twin T oscillator. These are very common RC oscillators. The Wayne-Bridge oscillator, where you have all these RC oscillators. Here we have the Wayne-Bridge oscillator. Take OSC as oscillator, right? Yes. And then we have the first shift oscillator, and then the T oscillator, right? And the T, that is twin T oscillator, twin T oscillators. These are the common ones that we have as RC oscillators. So we're going to discuss one out of it. And you know that RC feedback oscillators are used for frequencies not up to 1 megahertz. Any frequency that is more than 1 megahertz, any frequency that is more than 1 megahertz, RC oscillators are not used for. RC oscillators are used for frequencies less than 1 megahertz. Less than 1 megahertz. Any frequency that is more than 1 megahertz, you can't use an RC oscillator. Are you getting my point? So if you are doing any design and you have a cost to use an oscillator and you are using RC oscillator and your frequency is 2 megahertz or 1.5, that circuit will not work. That's a practical thing. It will not work. You only waste your time, waste your energy, waste your resources. At the end of the day, go and give prayer point in the church. Yes. There are things that we pray for, sometimes we don't have results. We start blaming God. But because we have taken the wrong approach. That's it. So let us look at the Wayne-Bridge oscillator. The Wayne-Bridge oscillator here is one of the RC circuit oscillators that were found on board. And I think I should clean the board this side, right? So now this one has a diagram that looks like this. One, we're discussing the Wayne-Bridge oscillator, right?
Yes.
The Wayne-Bridge oscillator. Every circuit you are drawing, always ground it very well, okay? Always ground your circuit very well, okay? If you don't ground it and you're having issues, don't blame anybody. There are circuits that if you don't follow the ground, it will not work. And you'll be here complaining. C1, C2, R1, R2. No, I don't know. I think it's R1, C2, sorry. R1. This should be R1, C2, just C1 here, based on arrangement here. So now here you have your V out, and then here is your V in, okay? And then the response curve of the circuit looks like this. This is now your V out, your V in, and then the resonant frequency with respect to the frequency here. This response curve, this one is the response curve. Response curve of this circuit, okay? This is the circuit of Wayne bridge, and this is the response curve, okay? In this circuit, there's something that we need to understand. It is a lead lag circuit. It is a lead. It is a lead lag circuit, right? It's a lead lag circuit. I'm going to explain in details, don't worry. In this circuit, R1 and C1 together form the portion of the circuit. R1 and C1 forms the lag portion of the circuit. Is the lag portion, and this is what the lead portion. Have you seen it? R1 and C1 forms the lag portion, and C2 and R2 forms the lead portion of the circuit. The operation of this lead lag circuit is shown at lower frequencies. At lower what? Frequencies. The lead circuit dominates due to the high reactance of C2. Let me start. There's something you need to know about this. C2. This is the equation for the reactance of this component here. So at lower frequencies, the resistance increase. This is the capacity reactance of the circuit increases. Do you see that? At lower frequencies, the lead circuit dominates due to the high reactance. When the frequency is low, the reactance of C2 increases. Have you seen it? This is an inverse now. If the frequency is low, the reactance will increase, the reactance of the circuit will increase for the lead portion. And if the frequency is high, then the reactance will decrease for the lead circuit, part of the circuit. Huh? As the frequency increases, the capacity reactance of C2 decreases, thus allowing the output voltage to increase. If the frequency continues to increase, the resistance of that circuit on that capacitor, that the reactance will begin to decrease. And then high output. Mind you, the lower the resistance, the higher the current. And current is proportional to the voltage. Agreed?
Yes.
Good. As for specified frequencies, the response of the lag circuit takes over. And the decreasing value of Cx1 causes the output voltage to decrease. So if you have another one, RC1 now. FC1 equals to 1 over 2 pi FC2. If this one begins to decrease, this one will increase. If the reactance of the circuit or the lag begins to increase, then the F will also increase. And the response curve is shown here. This is the response curve of the circuit. This is the response curve. This is the resonant frequency. This is the voltage in, this is the voltage out. This is a graph of V out against the frequency. Have you seen it? Yes. Mm-hmm. At this point, the attenuation. At this point, the attenuation is V out by V in. Agreed? Yes. V out by a V in. Or the circuit is V out by a V in, which is equals to 1 over 3, which is equals to 1 over 3. If R1 equals to R2, if R1 equals to R2, and FC1 equals to FC, and FC1 equals to FC2. That is, when you look at the frequency of, those of you that studied are very good in physics. For any resonance to take place, the graph of the reactances must equate at a level. Like when you have a supply and a demand curve, where they meet, what happens at that point? Demand and the supply curve, when they intersect, what happens? When they intersect like this point, what happens here? So we don't have economic students here. You don't know? Okay, if you have a graph like this, what will happen is that if this is the demand and this is the supply, it will show that the supply is constant and the demand is continuous. Yes. In other words, from this relationship here, we are going to have V out, V in equals to 1 over 3. Therefore, V out plus V in equals to 1 by 3. And the formula for the resonant frequency is given here as resonant frequency formula is FR equals to what? 1 over 2 pi RC. 2 pi R what? C. That is the formula for it. That is, in this case, the demand and the supply at this point are almost same. You are supplying, you understand, and the demand is also equating at this level. But practically looking at the graph, you can see that the supply is just rising up. You understand? And the demand, you understand? Maybe at 50 kobo. 50 kobo. The supply is constant at 50 kobo. You understand? But the demand has risen from 0 to maybe 2, or how do I put it in cost, in terms of monetary terms. But at this point, the demand equals to the supply. That is just the thing. Demand and supply equilibrium. Equilibrium. Yes. That's what I've been looking forward to say. It reaches an equilibrium state. At that point, customers will no longer be complaining of high cost of items, because the price at that level becomes steady. The price at that stage becomes very steady. Nobody will complain because they feel that the amount of oil I'm buying, the demand is that the amount of oil is supplied and what I'm buying, no, it's worth having that, paying that amount of money.
I went to 65 naira.
Huh?
I went to 1 liter with 65 naira.
Before what? That's what you're using economics by who? In those days, not today. In this new generation, you can write 800 naira per liter. And then you'll be right, okay? But not today. Okay. So, and the conditions for this oscillation to take place is that the first shift must be equal to 0 and what? The attenuation is what? 1/3. And the gain of the circuit must be equal to 1. If oscillators, right? We have discussed the wave bridge oscillator. Now we'll look at the first shift oscillator. The first shift oscillator uses an op amp. It uses what? With a feedback resistor. And then the wave bridge, the RC is attached. Not really the wave bridge, but it appears to be like that, but not really like that. Okay? That is the diagram for a phase shift oscillator, okay? You can see that in the phase shift oscillator we're having resistors and capacitors. Is it not an RC? R means what? Resistance, and then C means capacitance. So automatically it is an RC oscillator. There is something, each of the 3 RC circuits, how many of them are there? C1, R1, C2, R2, C3, R3, right? 3 RCs circuits are there. Circuits in the feedback loop can provide a maximum phase shift of 90 degrees. Each of them provides a phase shift of 90 degrees. And oscillations are caused at the frequency where the total phase shift is what? 180 degrees. Oscillations are caused here when the frequency is about 180 degrees on this circuit. So, have you gotten that in your head? And you know that the feedback terminal is connected to the inversion terminal. That is the negative terminal. Am I correct? Okay, I didn't write the positive. This is the inversion and this is the non-inversion or inverting terminal. It's connected to the inverting terminal. Okay? It provides additional 180 degrees to meet the requirement for oscillation of the circuit of a 360 degrees or 0 degrees. Most of the oscillators, the condition for phase shift is 0 degrees. Either 360 degrees or 0 degrees. That's a condition. Phase shift around the feedback loop. So in this case, the attenuation B of the 3 section RC feedback is B equals to 1/29, 1/29. The attenuation of the feedback loop B equals to 1/29. Standard for this series, okay? Where B equals to R31. The derivation of this visual result is given in to meet the greater than unity loop gain requirement. The closed loop voltage gain of the op-amp must be greater than 29 set by RF and R3. RF and R3 will actually set up the gain of this system. The frequency of oscillation FR is also could be derived from this very circuit that I have on the board here. Where R1 R equals, where R equals to R2, R3, and this and that. On this, we're in a condition where, when R equals to R1, equals to R2, equals to R3, and C equals to C1, equals to C2, equals to C3. At this point, there will be an oscillation, and it will take place very well. Okay? There's a calculation that I want you to do on that. So the resonant frequency of the circuit, is 2 pi 6 RC, root 2 6 RC. Resonant frequency FR of the circuit. CCT means circuit, right?
Yes.
FR equals to 1 over 2 pi root 6 RC. This is the formula. Okay? So let us solve a problem that will relate what we're doing here. We're going to solve a problem in respect to the this space shift oscillator now. We're going to solve just one problem, okay? The example here is the question says determine the value of RF, that is feedback resistor, necessary for the circuit in the above figure that is on the board, right? To operate as an oscillator. Also determine the frequency of oscillation. So now I told you that the attenuation here also gotten by RF over R3. Okay? RF by R3 equals to what? That's the relationship that holds for it. So now, what are we going to do? Ideally, if we are to get this working, what are we going to do? So this should be R3 all over RF. So if we are to get this, should I say this is 1? This is 2, right? Then from 1 over 29 equals to R3 over R what? F. So 29 would be what? If I make it 29 distribution, it would be RF by R3. Agreed?
Yes.
Huh? So if we really want to get the RF, what do we do to get the RF? Now let me give the values for the components that are there. That's 10K. This one is close to 10K from the question. This is 10K. This is 10K. This is 0.01 micro F. 0.01 microfarad. 0.01 microfarad. This is not given. And you are expected to know the value. So what are you going to do? Where R3 equals to 10K, right? Equals to 10. Is it not 10K?
Yes.
It's 10K. Because you are told to find the value of RF, which is the feedback resistor. Okay? So the feedback resistor now will be RF equals to 29 dot R3, which is equals to what? 29 times 10 times 10 raised to 3, which will be what? 290K kilo ohms, right? Is it not 290? 290K. Now, if the value of this is now 1, the feedback resistance is 290 kilo ohms. Then question number 2. The question number 2 is requesting for the resonant frequency of the circuit, the frequency of oscillation of the circuit. So we're going to apply this formula here, this very formula. This is the formula for the resonant frequency, okay? And we're told that FR equals to 1 over 2 pi square root of 6 RC, where C1 equals to C2 equals to C3, and R1 equals to R2 equals to R3. So when you have this condition, so each value of this component will be selected just once, and that will be FR equals to 1 over 2 pi square root of 6 times 10 K, 10 times 10 raised to 3 because of K, times 0.01 times 10 raised to minus 6, that's micro. Are we there? Yes. So when you have that, what will happen is that this is 10 raised to 4 already here. And this will be 10 raised to minus 1. Let us put it in a way that it will be easy for us to. 2 pi root 6 times 10 raised to 4, because you are taking this 0 out. Or you can make it 1 times 10 raised to 4. If you want to make it easy for you. This is 1, 2. This one becomes 1 times 10 raised to minus 8. You are moving the point 2 times to the right, okay? Because 2 raised to minus 8. So you can delete this and delete this. You will be left with minus 4 here. Abi? So when that happens, you have FR equals to 1 over 2 pi square root of 6 times 1 times 10 raised to minus 4. So you have to get the square root of this number. And if you do that, the result you are going to get will be 6.5 kilohertz. It will be 6.5 kilohertz. That will be the solution to the problem. Okay? Too difficult or too easy? Huh? So we're going to look at oscillators with LC feedback circuits. Oscillators with, we have treated 2 oscillators already in the RC. Okay? You're sleeping, you? You're sleeping. Don't worry, we'll soon finish. We're really moving at the right frequency, and I believe everything will go down well. Huh? Stop sleeping. So oscillators with LC feedback circuits. When you talk of LC feedback, we're looking at a situation whereby an inductor and a capacitor is connected to the circuit, where you have the inductance and the capacitance therein. Okay? And the common types of, and this type of oscillator is used for frequencies that are about 1 megahertz or above. Okay? And the types of RC circuits that we have the Kopich oscillator, we have the Hartley oscillator, we have the Clap oscillator, we have the Armstrong oscillator, we have the crystal controlled oscillator. But we shall be discussing 2 here. We are going to discuss the Kopich oscillator, also the Hartley oscillator, or probably touch the Clap oscillator, which is a very common oscillator around us. But most of the circuits that you see use the Kopich or the Hartley. Use the Kopich or the Hartley oscillators. Are you getting me? Yes. This type of oscillators use an LC circuit in the feedback loop. Here, the feedback in the RC, resistors and capacitors are used in the feedback. Here, you are going to use inductors and capacitors as feedback loops, and these are called tanker circuits. Here, the L and C is called tanker circuit. I'm going to draw it on the board, and you'll see it. And to act as a resonant filter, that passes only the desired frequency of what? Oscillation. So let me draw quickly the Kopich oscillator and explain how it works, and probably try to look at some few things that are required about it. I think I'm free to clean it, right? Yes. LC oscillators. And we're specifically looking at what? Kopich oscillator. pulpit what? Oscillator. Pulpit oscillator. The pulpit oscillator has a circuit that looks like this. I told you that oscillators use transistors, Abi? Yeah. This one is using a transistor. And this one is a resistor. It's connected. And the function of this capacitor here is for decoupling. And there's another resistor. There's connected here to base bias the something. And this goes to plus VCC. And this is the emitter. We're using an NPN transistor, 10Q1. And we may have a feedback loop. And this feedback loop is going to have two capacitors and one inductor because it's a pulpit. So if the output is taken from here, which is from the collector, this is the capacitor. This one counts down. You have an inductor connected. You have a capacitor connected, another capacitor connected. And then this goes to, this is grounded, this is grounded. And this is a capacitor connected at the inputs, and this one comes in here. So, this is the diagram of a pulpit oscillator. The oscillator is using a transistor, right? It's using a transistor. And from the numbering of this circuit, let me say this is R1, R2, R3, R4, C1, C2, L, C3, C4, C5, and this is your output. Are you seeing any input here? Huh? No. Because I told you that oscillators are circuits that don't necessarily need inputs. They need output. When that is generated, when the power is fed in, the power is not really the input to power supply. The VCC is not really necessarily the input to. If not, why is it that your amplifiers are powered and you still need a microphone to connect at the input? Is it the same thing? No. So oscillators are not like that. So looking at this circuit, what you are going to experience is this. The function of the resistor R1 and R2 is to base bias the base of this resistor, this transistor. This is B, base is B. Emitter is E, denoted E, and then collector C. And this is an NPN transistor. And the function of this transistor, one, is to act as an amplifier here. I told you that oscillators do have amplifiers, right? Yeah. You may have an op-amp as an amplifier. Like the RC, we're using the op-amp, right? Where you have the phase shift using op-amp. Where you have the three RCs. And then this one here, we just have the transistor, a single transistor as the amplifier. So when the oscillation starts here, this is when the oscillation starts. When the oscillation starts here, because of the tanker circuit, this circuit you see here is referred to as tanker circuit. It's referred to as tanker circuit in electronics. Or refer to this as tanker circuit. This is tanker circuit. It's a circuit that can generate frequencies. And how is the circuit generating frequencies? You may not understand, but I can prove to you tentatively that it can do that. If I should say C1 equals to C2 equals to C, C2, or C, and then I'm taking the value of the inductance as L. If I consider the capacity reactance of XC equals to XL, then the value of XC is what? 1 over 2 pi FC. FC equals to 2 pi FL. Are you seeing what I'm doing? Huh? Yes. If I attempt to cross multiply, because I just want to prove what is happening here. here. Huh? If not, this C1 and C2 are connected in series. They are connected in series. And if you want to go to the total capacitance or capacitors connected in series, the formula is CT. Is the answer to this question here will be CT equals to C1, C2 over C1 plus C2. This will be the solution. But if the values are equal, for instance 1, then you will have this kind of thing. Then this is 2 pi Fc times 2 pi Fl equals to 1. Am I right? Huh? I want to prove something. I'm going to explain the secret. I just want to prove something for you here. So now, if 2 times 2, if this is going to multiply itself, you are going to have 4, 2 by 2, pi squared, F squared, Cl equals to what? 1. But your problem is the frequency, right? It's the frequency that you want to deal with. So this will give you F squared, or you divide both sides by what? Both sides by 4 pi squared Cl. Then you have 4 pi squared F squared Cl all over 4 pi squared Cl equals to 1 all over 4 pi squared Cl. You know that 4 will cancel itself, right? Pi will cancel itself. The frequency will not cancel because there's no frequency down here. The capacitance, inductance, and all these ones will cancel. Then you have your F squared. That is 1 all over 4 pi squared F squared F. No, this is 4 pi squared. That's all. Squared pi squared Cl.